What if everything you thought you knew about reality was just the tip of the cosmic iceberg? Picture this: somewhere out there, in the infinite expanse of space, time stretches like taffy when you move faster. Black holes swallow information into oblivion, and particles separated by light years dance in perfect, instantaneous harmony. This isn't science fiction. This is the universe as it truly behaves, a place where the rules we take for granted on Earth unravel into paradoxes so strange they'll make you question the very fabric of existence. We like to think we've got a handle on how things work. Gravity pulls us down, time ticks forward, and objects can't be in two places at once. But the moment we step beyond our planet, the cosmos laughs at our assumptions. Take the twin paradox, where one astronaut ages slower than their identical sibling just by traveling near light speed, or the Fermi Paradox, which stares back at us with a chilling question: if the universe is teeming with potential for life, why does it feel so hauntingly empty? These aren't just quirky thought experiments. They're glaring signs that reality is far weirder, far more mysterious than our everyday logic can grasp. That's exactly what we're diving into today: 20 of space's most mind-bending paradoxes, each one a cosmic riddle that defies common sense. Some will bend your perception of time. Others will make you wonder if the universe is playing tricks on us, and a few might just leave you staring at the night sky, realizing how much we still don't, and maybe can't understand. So buckle up. By the end of this journey, you won't just see space differently, you'll see everything differently, because out there in the great unknown, the impossible isn't just possible, it's the norm. The Fermi Paradox is one of those cosmic riddles that starts simple and then burrows deep into your mind, leaving you with more questions than answers. We know the numbers: billions of galaxies, trillions of stars, countless planets in habitable zones. So where is everybody? Statistically, the universe should be buzzing with civilizations, yet all we hear is silence. It's like throwing a party for the entire neighborhood and no one shows up. One explanation is the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar communication. Maybe it's the difficulty of evolving complex life, or perhaps civilizations inevitably wipe themselves out before they can spread beyond their home planet. If that's true, the chilling question becomes: have we already passed the filter, or is it still ahead of us, lurking in our future? Then there's the zoo hypothesis, the idea that advanced civilizations know we're here but choose not to interfere, observing us like animals in a cosmic wildlife preserve. Or maybe the universe is just too vast, and signals take so long to travel that civilizations blink out before their messages ever reach us. Some even suggest that we're alone, that Earth is a rare, miraculous fluke in an otherwise lifeless expanse. Whatever the answer, the Fermi Paradox forces us to confront our own fragility. Are we destined to fade into cosmic obscurity, or is there a future where humanity finally breaks the silence? For now, the stars keep their secrets, and the question lingers like an echo in the void. Now imagine watching your identical twin board a spaceship and blast off at nearly the speed of light, only to return decades later looking barely older than the day they left. Meanwhile, you've lived a full lifetime, wrinkles, gray hair, and all. This isn't some futuristic fairy tale. It's the twin paradox, one of Einstein's most startling predictions, and it flips everything we assume about time upside down. At the heart of this paradox is relativity's bombshell revelation. Time isn't universal. It stretches and compresses like rubber depending on how fast you're moving. The faster you go, the slower your clock ticks compared to someone standing still. Atomic clocks flown on jets have proven this. After racing around the Earth, they show slightly less elapsed time than identical clocks on the ground. Now scale that up to near light speed travel, and the effect becomes dramatic. A twin making a round trip to a nearby star might return to find their Earth-bound sibling has aged decades more. But here's where it gets twisty. Why doesn't the traveling twin see Earth's clocks moving just as slowly? The key is acceleration. The spaceship twin feels real forces during takeoff, turnaround, and landing, breaking the symmetry between them. Relativity isn't just about speed, it's about whose frame of reference gets to call itself at rest. This paradox forces us to abandon the comforting idea of a single, universal now. Your present moment could be someone else's distant past or future, depending on how you're moving. It means aging isn't just biological, it's woven into the very fabric of space-time. Future interstellar travelers might return to find entire civilizations risen and fallen during what felt like a brief voyage. Perhaps most unsettling is what this says about time's illusion of flow. We experience it as an unstoppable river, but relativity paints a stranger picture, a vast, frozen landscape where past, present, and future coexist, with motion determining which slice you perceive. The twin paradox isn't just a quirk of physics. It's a gateway to understanding that time, as we feel it, might be the universe's most convincing mirage. Black holes aren't just cosmic vacuum cleaners, they're the universe's ultimate paradox, tearing apart the very laws of physics at their edges. According to Einstein's general relativity, once something crosses a black hole's event horizon, it's gone forever, crushed into a singularity where space and time cease to make sense. But quantum mechanics, the rulebook for the subatomic world, insists that information, the fundamental details of every particle's existence, can never truly be destroyed. So when a black hole swallows a star, or even just a single atom, where does that information go? This contradiction isn't just a technicality. It's a battle between two pillars of modern physics, and the stakes couldn't be higher. Stephen Hawking threw the first punch in this debate when he discovered black holes aren't entirely black. They slowly leak energy, a faint glow we now call Hawking radiation. Over unimaginable eons, this radiation causes black holes to evaporate, vanishing entirely. But here's the catch. Hawking's early calculations suggested the radiation was random, carrying no trace of the information swallowed by the black hole. If that were true, the information would be erased from the universe, violating quantum mechanics' sacred principle of information conservation. Physicists were left scratching their heads. Either general relativity was wrong, quantum mechanics was flawed, or something even weirder was happening. The controversy sparked decades of fierce debate, with one camp arguing information is irretrievably lost, while others scrambled to find loopholes. Then came the holographic principle, a radical idea suggesting all the information swallowed by a black hole isn't lost but smeared across its event horizon like a cosmic fingerprint. Imagine throwing a book into a fire, but instead of burning away, the words rearrange themselves into a two-dimensional code on the surface of the flames. That's the essence of this theory. The information isn't gone, just transformed in ways we're still struggling to decode. Yet even this elegant solution has its skeptics. Some theorists propose that black holes don't evaporate completely but leave behind tiny remnants, information-packed relics smaller than an atom. Others suggest the information escapes through hidden wormholes or parallel universes, weaving a multiverse into the fabric of the paradox. The wildest idea, that black holes are cosmic backdoors, their interiors leading not to oblivion but to entirely new regions of space-time, with the information reborn somewhere else in the cosmos. What makes this paradox so thrilling is that it's not just about black holes, it's a clue to a deeper theory of everything, a framework that could finally unify gravity and quantum mechanics. Every proposed solution forces us to rethink reality in ways that sound like science fiction. Maybe spacetime isn't fundamental, but emerges from something more basic, like pixels on a cosmic screen. Or perhaps causality itself bends in the presence of a black hole, allowing information to exist in multiple states at once. One thing's certain, until we crack this paradox, our understanding of the universe remains incomplete. Black holes aren't just celestial oddities, they're cosmic teachers, revealing where our best theories break down. And in those breakdowns, hidden in the chaos of conflicting physics, might lie the next great revolution in science. Imagine pointing a camera at a single electron, only to watch it suddenly change its behavior, not because of any physical force, but simply because you looked. This is the observer effect, one of quantum mechanics' most unsettling revelations. At the subatomic level, particles don't have definite properties until we measure them. It's as if reality itself is shy, rearranging its behavior the moment we try to pin it down. The classic double-slit experiment lays this paradox bare. When particles like electrons are fired one by one at a barrier with two slits, they create an interference pattern on the other side, as if each particle is passing through both slits simultaneously, a wave-like behavior. But the instant scientists place a detector to observe which slit each electron actually goes through, the interference pattern vanishes. The particles start behaving like tiny billiard balls, as if they've been caught red-handed and decide to act normal. What's truly bizarre is that this isn't a limitation of our technology. It's baked into the fabric of reality. The act of measurement forces quantum systems to choose a state, collapsing what was once a haze of possibilities into a concrete outcome. Some interpretations suggest particles exist in multiple states at once, a superposition until observation forces them to pick one. Others propose that every possible outcome branches off into parallel universes, with each measurement locking us into a single timeline. This raises a haunting question. Is there an objective universe at all, or does reality only take shape when conscious observers interact with it? The implications ripple far beyond the lab. If observation alters the observed, then the distinction between the observer and the observed starts to blur. Are we passive witnesses to the cosmos or active participants in its creation? Even the tools we use to measure particles can't escape scrutiny. The very light photons we rely on to see an electron inevitably disturb it, like trying to measure the ripples in a pond by poking it with a stick. Heisenberg's uncertainty principle codifies this, stating that the more precisely we measure a particle's position, the less we can know about its momentum, and vice versa. It's not a lack of skill, it's a fundamental limit written into the universe's code. The observer effect forces us to rethink not just physics, but philosophy. If reality is this malleable at the smallest scales, what does that say about the solid, predictable world we experience every day? Some theorists argue that quantum weirdness averages out in larger objects like cats or planets. But others wonder if consciousness itself plays a role in shaping reality, a notion that edges tantalizingly close to age-old questions about the relationship between mind and matter. One thing's certain, quantum mechanics refuses to let us be mere spectators. Every time we peer into its depths, we're reminded that the universe isn't just stranger than we imagine, it's stranger than we can imagine. And in that strangeness lies a profound truth. The act of seeking answers might just be what creates them. What if you could step into a time machine, travel to the past, and stop your own grandfather from ever meeting your grandmother? At first glance, it sounds like a darkly amusing thought experiment. but the grandfather paradox cuts straight to the heart of why time travel might be impossible, or at least nothing like we imagine. The moment you prevent your own birth, you create an unsolvable loop. If you were never born, you couldn't have traveled back to change history in the first place. So how could the past already be altered by someone who, logically, shouldn't exist? This isn't just a puzzle for science fiction. Physicists and philosophers have wrestled with it for decades because it exposes a fundamental tension between cause and effect. Our everyday experience tells us that events unfold in a straight line, one thing leads to another in an unbroken chain. But if time travel were real, that chain could twist into knots, with effects preceding causes or erasing them entirely. Some theories try to sidestep the paradox by proposing that any changes you make in the past would simply create a new, parallel timeline, leaving the original history untouched. In this multiverse scenario, you might erase your own existence in one branch of reality while remaining perfectly intact in another. It's a tidy solution, but it raises its own questions. If every decision spawns alternate universes, where does it end? Then there's the idea of self-correcting events, sometimes called the Bootstrap Paradox. Imagine going back in time to give Shakespeare a copy of his own plays before he writes them. Where did those plays truly originate? There's no original source, just an infinite loop with no beginning. Some theorists argue the universe might enforce consistency, bending events subtly to prevent outright contradictions. Maybe your attempts to interfere with the past would always fail, thwarted by improbable accidents or sudden changes of heart. But here's the deepest irony. The grandfather paradox doesn't just challenge time travel, it challenges our understanding of time itself. Is the past truly fixed, or is it as malleable as the future? Could there be layers of reality where cause and effect aren't locked in place? Or does the mere existence of this paradox prove that traveling backward through time is a fantasy, no matter how much physics teases us with theoretical possibilities like wormholes or cosmic strings? Perhaps the most unsettling takeaway is that time, as we perceive it, might be an illusion, a stubbornly one-directional flow that only feels absolute because we're trapped within it. The grandfather paradox doesn't just ask whether we can change history. It asks whether history is even something that can be changed, or if every moment is already set in stone, woven into a universe where free will and fate are two sides of the same coin. Until we crack this riddle, time travel remains the ultimate what if, a mirror held up to our deepest assumptions about reality itself. Spiral galaxies should fly apart. That's the unsettling truth astronomers stumbled upon decades ago when they measured how fast stars orbit their centers. According to Newton's laws, the outer stars in a galaxy like our Milky Way should move slower than the inner ones, just as Pluto trudges around the Sun far more sluggishly than Mercury. But observations reveal something bizarre. Stars at the galaxy's edge whip around just as fast as those near the middle, as if some unseen hand is gripping them, preventing them from flinging off into the void. The numbers don't add up. There simply isn't enough visible matter, stars, gas, dust, to generate the gravity needed to hold these galaxies together. This discrepancy isn't a minor accounting error. It's a cosmic crisis. Either our understanding of gravity is fundamentally wrong, or the universe is filled with something invisible, something that doesn't emit, absorb, or reflect light, yet outweighs all the ordinary matter we can see by a staggering 5-to-1 ratio. Scientists call this phantom substance dark matter, and its existence would rewrite the recipe of the cosmos. Imagine baking a cake where 4/5 of the ingredients are flavorless, odorless, and completely undetectable except by their weight. That's the universe we seem to live in. The evidence isn't just in galaxy rotations. dark matter's gravitational fingerprints appear everywhere, in the way light bends around galaxy clusters, in the intricate web of the cosmic microwave background, even in the very structure of the universe itself. Without it, galaxies wouldn't have had enough gravitational pull to form in the early universe. Yet despite its apparent omnipresence, dark matter remains maddeningly elusive. We've built detectors deep underground, shielded from cosmic rays, waiting for a single telltale collision between a dark matter particle and ordinary atoms. We've scanned the skies for gamma rays that might signal its annihilation. So far, nothing. This raises a provocative question: what if dark matter doesn't exist at all? A bold minority of physicists argue that instead of invoking invisible matter, we should modify our theory of gravity. Modified Newtonian dynamics, or MUND, suggests that gravity behaves differently at the vast, faint scales of galaxies than it does in our solar system. It's a radical idea, one that would upend Einstein's relativity, but it neatly explains galaxy rotations without hidden ingredients. The catch: MUND struggles to account for all the other evidence, like the bullet cluster, where two colliding galaxies seem to have left their dark matter halos trailing behind like cosmic ghosts. The stakes couldn't be higher. If dark matter is real, it's not just another particle, it's an entire shadow universe, a hidden architecture shaping everything we see. Some theories propose it's made of weakly interacting massive particles, or WIMP, left over from the Big Bang. Others suggest actions, ultra-light particles streaming through space like an invisible mist. There's even speculation about primordial black holes forged in the universe's first frantic seconds, but with every failed detection, the mystery deepens. Could dark matter interact with itself in ways we haven't imagined? Does it inhabit extra dimensions forever beyond our reach? Or is this the universe's way of telling us we've misunderstood gravity all along? The longer the search continues, the more this paradox forces us to confront an uncomfortable truth. We may be blind to most of reality, groping in the dark while the cosmos whispers its secrets just beyond our grasp. What if everything you perceive, the screen in front of you, the room around you, even your own memories, isn't real at all, but just a random flicker of atoms assembling by pure chance into a momentary illusion of self-awareness? This is the unsettling premise of the Boltzmann Brain paradox, a thought experiment so bizarre it makes you question whether anything can be trusted. The idea comes from Ludwig Boltzmann, a physicist who realized that in an infinite universe with infinite time, even the most improbable events must eventually happen. Given enough time, particles bouncing around at random could theoretically arrange themselves into a fully formed, conscious brain, complete with fabricated memories and a convincing hallucination of reality. And here's the kicker: statistically, it's far more likely for a single, fleeting Boltzmann brain to pop into existence than for an entire, orderly universe like ours to emerge and persist. So why do we find ourselves in a seemingly stable cosmos, surrounded by consistent laws of physics, rather than as isolated brains drifting in the void? That's the paradox. If randomness favors ephemeral flashes of consciousness over enduring reality, then the fact that we experience a coherent, structured world becomes inexplicable. Some interpretations suggest that our perception of time and continuity might itself be an illusion, that we could be momentary aberrations, destined to dissolve back into chaos the instant we stop observing. Others argue that the very existence of our complex universe, with its finely tuned constants, implies something deeper at work, perhaps undiscovered laws of physics or even a multiverse where countless realities coexist, making our ordered existence less improbable. The paradox doesn't just rattle our sense of reality, it exposes the fragility of human reasoning. If a Boltzmann brain's fabricated memories are indistinguishable from genuine experience, how could we ever prove we're not one? Science relies on the assumption that observations reflect an objective world, but this thought experiment turns that certainty on its head. It's like realizing the ground beneath your feet might be a hologram with no way to test its solidity without potentially triggering its collapse. Yet the Boltzmann Brain paradox isn't just a philosophical curiosity, it's a boundary marker for cosmology. If the universe truly is infinite and eternal, then probability demands that Boltzmann brains should vastly outnumber real minds. The fact that we don't observe this might hint that our universe isn't infinite after all, or that some fundamental principle prevents such randomness from dominating. Some theorists propose that the arrow of time, the one-way flow from past to future, acts as a safeguard, steering the cosmos away from chaotic fluctuations and toward order. Others suggest that consciousness itself might play a role in anchoring reality, though this veers into speculative territory. At its core, this paradox forces us to confront the limits of what we can know. Are we the products of a vast, ancient cosmos, or just fleeting accidents in a sea of entropy? The answer, if there is one, might lie in the intersection of quantum mechanics, cosmology, and the very nature of observation. Until then, the Boltzmann brain remains a humbling reminder that the universe's deepest truths might be stranger and more unsettling than we've dared to imagine. Picture this: you step outside on a clear night, look up, and instead of seeing a sky studded with stars, you're met with a blazing wall of light, every inch of darkness obliterated by the combined glow of countless suns. That's what the night sky should look like if the universe were infinite, unchanging, and filled with stars stretching endlessly in all directions. Yet when we gaze upward, we see darkness punctuated by pinpricks of light. This glaring contradiction is Olbers Paradox, a puzzle so profound it reshaped our understanding of the cosmos. Named after the astronomer Heinrich Olbers, who popularized it in the 19th century, the paradox seems simple at first. If stars are scattered uniformly across an infinite universe, then no matter which direction you look, your line of sight should eventually land on a star. Just like standing in an endless forest guarantees every gap between trees will eventually be blocked by another trunk. The entire sky should shine as brightly as the surface of the sun, bathing Earth in perpetual daylight. The fact that it doesn't suggest something fundamental is missing from that picture. The answer lies in two game-changing realizations. First, the universe isn't static, it's expanding. Distant galaxies are racing away from us, stretching the light they emit into longer, redder wavelengths that eventually fade beyond our ability to detect. This phenomenon, called redshift, means the light from the farthest stars hasn't just dimmed. In many cases, it's been stretched into oblivion, rendering those regions of space effectively invisible to our eyes. Second, and even more profound, the universe has a finite age. Light travels at a fixed speed, and the cosmos hasn't existed long enough for every star's glow to reach us. Imagine turning on a lamp in a cavernous, pitch-black room. The light hasn't yet filled every corner. In cosmic terms, we're still waiting for photons from the most distant reaches to arrive. The darkness between stars isn't empty. It's a time capsule, revealing how much of the universe remains beyond our view. This paradox didn't just solve a riddle about the night sky, it cracked open the door to modern cosmology. The realization that the universe had a beginning led directly to the Big Bang theory, while the discovery of its expansion upended centuries of belief in a steady, unchanging cosmos. It also forced us to confront the limits of our perception. The night sky isn't a map of the universe as it is, but a patchwork of light from different eras, some so ancient the stars that emitted it have long since died. But here's the twist: Olbers' paradox might not be fully resolved. Some theorists argue that even in an expanding, finite-age universe, the sky should still be brighter than it is, suggesting there could be deeper layers to this mystery. Perhaps interstellar dust absorbs some starlight, or maybe the distribution of stars isn't as uniform as we assume. Others wonder if the paradox hints at something even stranger, like a cosmos far larger than the observable universe, where light from the most distant regions will never reach us, no matter how long we wait. What makes this paradox so enduring isn't just the science it unlocked, but the humility it instills. That darkness above us isn't emptiness, it's evidence of a universe too vast, too dynamic, and too ancient for our ancestors to have imagined. Every time we look up at a starry sky, we're not just seeing light, we're seeing the echoes of a cosmic story still being written, one where the gaps between the stars hold as many secrets as the stars themselves. Ever heard the saying, "A watched pot never boils"? In the quantum realm, that old adage isn't just a quirk of impatience, it's a fundamental law of reality. Meet the quantum Zeno effect, one of physics' most counterintuitive phenomena, where the simple act of observing a system can lock it in place, like hitting pause on a movie mid-scene. This isn't just a theoretical curiosity. It's a window into how deeply measurement and reality are entangled at the smallest scales, challenging our most basic assumptions about cause and effect. The effect gets its name from an ancient Greek philosopher, Zeno of Elea, who famously argued that motion is an illusion. If you keep dividing a journey into smaller and smaller moments, you'll find an arrow never truly reaches its target. Quantum mechanics takes this idea and runs with it. Imagine an unstable atom on the verge of decaying. Left alone, it'll eventually break apart, releasing energy. But if you bombard it with rapid-fire observations, checking its state over and over, the atom freezes in place, as if the decay process gets reset with every glance. It's like trying to take a photo of a spinning fan. If you snap pictures fast enough, the blades appear motionless. This raises a dizzying question. Does the universe need conscious observers to define its behavior, or is there a deeper mechanism at work? Some interpretations suggest that measurement isn't passive, it actively forces quantum systems to pick a state, interrupting their natural evolution. Others argue the effect reveals a fundamental granularity to time itself, where reality operates in discrete steps rather than a smooth flow. Lab experiments have confirmed this phenomenon with trapped ions and photons, showing how frequent measurements can suppress chemical reactions or even keep particles suspended in mid-transition indefinitely. But the implications stretch far beyond the lab. If observation can alter reality's trajectory, does that mean consciousness plays a role in shaping the cosmos? Philosophers and physicists have wrestled with this for decades, with some proposing that the universe might be a participatory phenomenon, where observation and existence are two sides of the same coin. Skeptics counter that measurement doesn't require a human mind. Any interaction with the environment, like a stray photon collision, could trigger the same effect. The quantum Zeno effect also flips our understanding of stability on its head. Normally, we think of change as inevitable. Rocks erode, stars burn out, particles decay. Yet here's a scenario where vigilance itself becomes a tool for preservation. Scientists are already exploring practical applications, from error suppression in quantum computers to prolonging the life of delicate molecular states for medical imaging. It's as if the universe handed us a remote control for reality, with the pause button activated by the sheer act of looking. What makes this paradox so unsettling is how it blurs the line between the observer and the observed. We're used to thinking of the world as something that exists independently, ticking along whether we're watching or not. But the quantum Zeno effect suggests that at the most fundamental level, reality might be more like a dance, one where our attention, or even the environment's interference, sets the rhythm. It's a reminder that the universe doesn't just defy our intuitions, it revels in upending them, leaving us to wonder whether the pot never boils because we're watching, or if the watching itself is what keeps the fire alive. The Bootstrap Paradox twists time into a knot so tight, it threatens to unravel our most basic assumptions about reality. Picture this. A time traveler hands a young Shakespeare a leather-bound book containing all his future plays: Hamlet, Macbeth, Romeo and Juliet, before the bard has written a single word. Inspired, Shakespeare copies them verbatim, publishing works that later become legendary. Centuries pass, and those same plays end up in the hands of our time traveler, who whisks them back to deliver to Shakespeare. So here's the mind-bending question: who actually created these masterpieces? There's no original author, no point of origin, just an endless loop where the plays somehow exist without ever being truly written. This isn't just a quirky thought experiment. The Bootstrap Paradox forces us to confront whether cause and effect are as ironclad as we believe. Normally, we assume every event has a clear starting point, a first domino that sets the rest in motion. But in this scenario, the dominoes form a circle with no beginning or end. It's like a vinyl record spinning forever, its needle trapped in the same groove, producing music that seemingly comes from nowhere. Some physicists argue this paradox might not just be theoretical. If time travel to the past were possible, bootstrapped objects or information could become a feature of reality. Imagine finding a futuristic gadget in your basement, reverse engineering it, and then sending the blueprints back in time to your past self, who then builds the very device you originally found. The technology has no inventor, it just is a self-contained loop defying linear history. The implications ripple beyond time travel. Quantum mechanics already toys with similar ideas. Particles popping in and out of existence, virtual pairs borrowing energy from the future to exist briefly in the present. These phenomena flirt with the bootstrap concept on a microscopic scale. Could the universe itself contain bootstrapped elements, fundamental constants or laws that simply are because they've always been? Some interpretations of the Big Bang even suggest that the conditions for the universe's creation might have been generated by the universe itself, a cosmic Ouroboros swallowing its own tail. But here's where it gets truly unsettling. If information or objects can exist without origin, how do we trust any historical narrative? What if great inventions, philosophical ideas, or even religious texts were never created organically, but slipped backward through time, their true beginnings erased? The paradox doesn't just challenge physics, it threatens to upend our understanding of creativity, innovation, and even identity. After all, if you received a letter from your future self detailing your life's path, would you be following destiny or creating it? The Bootstrap Paradox leaves us stranded between two equally jarring possibilities. Either the universe has a way of enforcing consistency, weaving loops seamlessly into the fabric of reality, or our perception of cause and effect is a fragile illusion, a story we tell ourselves to make sense of a far stranger cosmos. Either way, one thing's clear: time, if it can be knotted like this, is nothing like the straight arrow we imagine. It might be a tangled thread, with some strands leading not just forward or backward, but in circles without end. Heat death sounds like the universe's final sigh, a distant future where all stars burn out, black holes evaporate, and every last bit of energy dissipates into a featureless, lukewarm void. It's the ultimate triumph of entropy, the relentless force that drives everything from melting ice cubes to dying stars toward disorder. But here's the catch: if the universe has a finite amount of energy, how can it take forever to reach this state of perfect equilibrium? shouldn't the clock run out at some point? This is the heat-death paradox, a cosmic riddle that exposes gaps in our understanding of time, infinity, and the very fabric of reality. At first glance, the math seems straightforward. Imagine pouring cream into coffee given enough time. The two will blend completely, reaching a uniform state where no further mixing is possible. The universe, according to thermodynamics, is headed for the same fate. But there's a glaring inconsistency. If the cosmos has a finite number of particles and a finite amount of energy, it should theoretically settle into equilibrium in a finite time, just like that coffee eventually stops swirling. Yet physicists argue heat-death isn't an event, it's an asymptotic endpoint, something the universe approaches but never quite reaches, like a car coasting toward a stop sign but never actually touching it. How does that make sense? One clue lies in the quantum realm. Even in what we'd call perfect equilibrium, tiny fluctuations can still occur, particles popping in and out of existence, brief surges of energy borrowed from the vacuum of space. These quantum hiccups mean true equilibrium might be impossible, like trying to smooth out a rug that keeps sprouting new wrinkles. Some theories suggest the universe could stave off heat-death indefinitely through these microscopic rebellions against entropy, creating pockets of temporary order in an otherwise lifeless expanse. Then there's the wild card of dark energy. If the universe keeps expanding at an accelerating rate, space itself might stretch so thin that particles become isolated, unable to interact at all. In this scenario, equilibrium isn't about everything blending. It's about everything becoming too scattered to ever mix again. But even here, the paradox lingers. If the universe is infinite in size, can it ever truly reach a uniform state? Or will there always be regions lagging behind, like patches of snow stubbornly refusing to melt? The most unsettling possibility is that our models are incomplete. What if entropy isn't the final word? Some theorists speculate that gravity, often sidelined in thermodynamics, could play an unexpected role. Black holes, for instance, warp spacetime so severely that they might recycle energy in ways we don't yet understand. Others propose that heat-death isn't an end but a reset, a dormant phase before quantum tunneling spawns a new Big Bang, restarting the cosmic cycle. What makes this paradox so profound isn't just the science, it's the philosophical weight. If the universe truly has infinite time, then statistically, anything that can happen will happen eventually. Given enough eons, could atoms randomly reassemble into conscious beings, reliving history in an endless loop? Or does infinity itself break down as a concept when applied to reality? The heat-death paradox doesn't just question the universe's fate, it forces us to ask whether our tools for predicting that fate are sharp enough to cut through the mysteries of eternity. One thing's certain, the answers, if they exist, lie in the uncharted territory where physics, philosophy, and the unknowable future collide. What if the universe around us, the stars, the laws of physics, even the thoughts in your head aren't fundamental reality, but lines of code in an unfathomably advanced simulation? This is the simulation argument, a paradox that takes the age-old question, what is real, and catapults it into the digital age. The idea isn't as far-fetched as it sounds. Think about how lifelike video games have become in just a few decades, characters with artificial emotions, virtual worlds governed by their own physics. Now project that forward 1,000 years or 1,000,000. If civilizations keep advancing, wouldn't they eventually create simulations indistinguishable from reality? And if so, how could we ever prove we're not inside one? The argument gained traction when philosopher Nick Bostrom framed it as a trilemma. Either advanced civilizations never reach the capability to run such simulations, they choose not to run them, or we're almost certainly living in one. The first two options feel shaky. Why wouldn't a species curious enough to develop simulation technology use it? That leaves the third possibility, a conclusion so unsettling it makes the plot of The Matrix look like a documentary. But here's where it gets twisty. If we're in a simulation, the rules of our universe might just be design choices. The speed of light, a built-in limit to prevent processing overload. Quantum indeterminacy, a way to render only what's being observed, like a video game that doesn't load distant terrain until you look. Even glitches in reality, déjà vu, Mandela effects could be explained as bugs in the system. Some theorists suggest we might find proof in the fabric of physics itself. If space-time has a finite resolution, like pixels on a screen, we could uncover its digital skeleton hidden in high-energy particle collisions or anomalies in cosmic radiation. Yet the paradox runs deeper than code. If simulations can host conscious minds, then the number of artificial beings would dwarf organic ones over time. Statistically, you're more likely to be one of the countless simulated entities than a rare original. This logic mirrors the Boltzmann Brain conundrum, another case where probability collides with perception. But unlike Boltzmann brains, the simulation hypothesis isn't purely philosophical. Tech moguls have funded research to test it, scanning the universe for signs of computational limits or repeating patterns that might reveal a programmed reality. Skeptics counter with Occam's razor. Why invent a cosmic computer when the universe explains itself just fine? Others argue that even an advanced civilization couldn't simulate every particle in real time. The energy requirements would be absurd. But what if the simulation only renders what we're observing, like a universe-scale version of lazy loading? Or maybe we're NPCs in a historical sim, our lives predetermined by some higher player's curiosity about 21st century Earth. The most haunting implication isn't about technology, it's about meaning. If we're simulated, do our choices matter? Is free will just an illusion baked into the program? Some philosophers suggest it doesn't change anything. Pain and joy feel just as real either way. Others see it as a secular kind of spirituality, a reminder that reality might be layered with truths we can't access from inside the system. Whether you find the idea terrifying or thrilling, the simulation argument forces us to confront the limits of knowledge. Proving we're not in a simulation might be impossible after all. Any evidence could itself be part of the simulation. That's the genius of this paradox. It turns the scientific method inside out, leaving us to wonder if the tools we use to uncover reality are just part of the illusion. In the end, the only certainty is uncertainty, and perhaps that's the point. The universe, real or simulated, loves a good mystery. What if the empty space around you wasn't actually empty at all, but a seething quantum soup of particles that only appear when you're moving at breakneck speeds? That's the mind-bending premise of the Unruh Effect, a paradox so strange it makes even seasoned physicists pause. Imagine two astronauts floating in the vacuum of space. One drifts peacefully, surrounded by what seems like perfect nothingness. The other fires a rocket pack, accelerating faster and faster, and suddenly, their sensors light up with particles popping into existence all around them, like fireflies materializing in the dark. Both are observing the same patch of universe, yet they're experiencing completely different realities. This isn't just a thought experiment. The Unruh Effect reveals a fundamental truth about quantum fields, the invisible scaffolding of reality. According to quantum theory, what we call empty space is anything but, even in a perfect vacuum, fields vibrate with fleeting energy, particles and antiparticles flickering in and out of existence too quickly to detect. Normally, these cancel each other out, leaving nothing behind. But for an accelerating observer, something extraordinary happens. the relentless motion distorts their perception of these quantum fluctuations, stretching some waves and compressing others until they freeze into detectable particles. It's like running through a rainstorm. If you sprint fast enough, you'll feel droplets hitting your face that were imperceptible at a stroll. The implications are staggering. It means there's no such thing as an objective vacuum, just different versions of empty depending on how you're moving. Temperature, too, gets dragged into the paradox. An accelerating observer doesn't just see particles, they feel heat, as if bathed in a warm glow. The faster they go, the hotter it gets, until near light speed, the vacuum would blaze like an oven. This eerie link between acceleration and temperature isn't coincidence. It's a clue that motion, energy, and quantum fields are deeply entangled, hinting at a universe where even the act of moving reshapes reality around you. But here's the twist: these particles aren't illusions. They're as real as anything else in quantum mechanics, with measurable energy and effects. If you could accelerate fast enough, say near the surface of a black hole, the Unruh radiation would be intense enough to cook you alive. This raises a haunting question. Is our perception of a calm, empty universe just an artifact of our slow, unaccelerated lives? Could beings living in extreme gravity or racing at relativistic speeds experience a cosmos teeming with particles we'll never see? The Unruh effect doesn't just challenge our ideas about space, it blurs the line between observation and creation. In quantum mechanics, particles often exist in fuzzy superpositions until measured. But here, the act of accelerating literally conjures them into being, as if motion itself is a kind of measurement. Some theorists speculate this could bridge general relativity and quantum theory, revealing how gravity emerges from quantum fields. Others see parallels to Hawking radiation, where black holes evaporate by producing particles at their edges, another case where motion and gravity rewrite the rules of emptiness. What makes this paradox so profound is how it turns a basic assumption on its head. We're used to thinking of reality as something that exists out there, independent of us. But the Unruh effect suggests the universe is more like a hall of mirrors, reflecting back not what's there, but what your motion allows you to see. It's a reminder that even the void isn't passive, it's dynamic, responsive, and far stranger than we've dared to imagine. The next time you stare into the night sky, remember, the silence of space might just be an illusion, one that shatters the moment you press the accelerator. Einstein called it spooky action at a distance, a phenomenon so unsettling, it made him question whether quantum mechanics could possibly be correct. Picture two electrons born from the same quantum event, forever linked no matter how far apart they drift. Measure one's spin as up, and its partner instantly becomes down, even if they're on opposite sides of the galaxy. No signal passes between them, no force connects them, yet somehow they act in perfect, instantaneous harmony, as if space between them doesn't exist. This is the Einstein-Podolsky-Rosen Paradox, a puzzle that cuts to the heart of reality's deepest mysteries. At first glance, this seems to violate Einstein's own theory of relativity, which declares nothing can outtrace light. Information transfer should take time, yet here, particles communicate faster than any cosmic speed limit allows. The key lies in what's actually being shared. Unlike a radio signal carrying a message, entangled particles don't transmit energy or matter. Instead, their properties remain undetermined until measured, like a pair of dice that only settle on numbers the moment you peak. The eerie part, those outcomes are always correlated, as if the dice share a hidden agreement. This challenges our most basic notions of locality, the idea that objects are only influenced by their immediate surroundings. In the quantum realm, particles appear to ignore distance entirely. operating as parts of a single, indivisible system. It's like having two coins that always land on opposite faces when flipped, whether they're in the same room or on opposite ends of the universe. Einstein argued this meant quantum theory was incomplete, that there must be hidden variables directing the particles' behavior behind the scenes, but decades later, experiments crushed that hope. When physicists tested entangled particles, the correlations held firm, proving no local hidden variables could explain the results. The implications ripple far beyond particles in a lab. If quantum entanglement holds across vast distances, could the universe itself be woven together by invisible threads of connection? Some interpretations suggest all particles were once packed together at the Big Bang, leaving remnants of that primordial intimacy even as space expanded. Others propose that entanglement creates a hidden layer of reality, where separateness is an illusion and everything is fundamentally linked. Yet the paradox persists. How can measurements here and now affect something infinitely far away without breaking causality? One radical answer is that the particles aren't truly separate, that space is just a stage, and the real action happens in a dimension where distance doesn't apply. Another possibility is that the universe knows the outcome in advance, with every measurement just revealing a pre-written script, or perhaps causality itself flows backward, with future observations shaping past events in a loop that defies linear time. What makes this paradox so electrifying is how it forces us to choose between two equally jarring options. Either the universe allows faster-than-light connections that relativity can't explain, or our understanding of reality is missing something profound. Quantum mechanics has passed every test thrown at it, yet it dances on the edge of logic, whispering secrets about a cosmos far stranger than we've imagined. Every time we peer deeper into the quantum world, we're left wondering, is the spookiness a bug in our theories or a feature of the universe itself? You open a box expecting to find a cat, either purring contentedly or, tragically, no longer alive. But according to quantum mechanics, until you lift that lid, the cat exists in a surreal superposition of both states at once, alive and dead. This is Schrödinger's infamous thought experiment, a paradox so bizarre it turns a simple pet into a philosophical battleground between the quantum and classical worlds. At its core, the scenario isn't about feline survival, it's a scalpel slicing into the heart of quantum theory's strangest prediction. In the microscopic realm, particles like electrons can occupy multiple states simultaneously, a phenomenon called superposition. Only when measured do they collapse into a single reality. Schrödinger's genius, or perhaps his mischief, was scaling this quantum quirk up to everyday objects. Imagine rigging a box with a vial of poison, a radioactive atom, and a Geiger counter. If the atom decays, the counter triggers the poison, killing the cat. But quantum rules say the atom exists in a blended state of decayed and undecayed until observed. By extension, the cat's fate remains undecided too, oscillating between life and death like a cosmic coin mid-flip. The paradox isn't just a playful jab at quantum mechanics, it's a spotlight on the glaring disconnect between the rules governing atoms and the world we experience. Why don't we exist in superpositions? Why does observation wield such power over reality? Some interpretations suggest that quantum effects do scale up, but they're too fragile to survive the chaos of macroscopic environments. A cat, with its trillions of interacting particles, effectively measures itself, collapsing superposition faster than we could ever observe. Others propose that consciousness itself is the trigger, that reality splits into parallel branches with each observation, one where the cat lives and another where it dies. But here's where it gets even stranger. Modern experiments with tiny diamonds and even viruses have pushed superposition into the visible world, proving quantum weirdness isn't confined to atoms. Yet the line between quantum and classical remains blurry. Is it size that matters, complexity, or is the universe somehow aware of the difference, enforcing one set of rules for the small and another for the large? Schrödinger's cat endures because it forces us to confront the unsettling idea that reality might not be as solid as it seems. The box isn't just a container, it's a metaphor for the limits of human intuition. Every time we try to peek inside, we're reminded that the universe plays by rules far wilder than our everyday logic can grasp. And perhaps that's the experiment's real lesson. The act of looking doesn't just reveal reality, it might just create it. The vacuum of space isn't just empty, it's a seething ocean of energy, a quantum frenzy that should, by all calculations, be powerful enough to rip the universe apart. Yet when physicists crunch the numbers, they're left staring at a result so absurd it's been called the worst theoretical prediction in the history of science. According to quantum field theory, the energy density of empty space, what we call the vacuum, should be a staggering 120 orders of magnitude stronger than what we actually observe. To put that incomprehensible number into perspective, it's like predicting a tsunami and instead finding a single ripple in a teacup. This colossal mismatch isn't just a minor error. It's the vacuum catastrophe, a paradox so glaring it threatens to unravel our understanding of reality itself. So where does this phantom energy come from? Quantum mechanics tells us that even in a perfect vacuum, particles and antiparticles constantly flicker into existence, borrowing energy from the void before annihilating each other in bursts of activity. These fleeting fluctuations generate what's known as zero-point energy, a background hum of the cosmos that should, in theory, fill every cubic centimeter of space with enough power to bend spacetime into knots. Yet when we look at the universe, we see none of this apocalyptic curvature. The cosmos expands calmly, almost as if it's ignoring the quantum chaos bubbling beneath the surface. The disconnect is so severe that it suggests one of two terrifying possibilities. Either our math is catastrophically wrong, or we're missing something fundamental about how gravity interacts with the quantum world. Some theorists argue that unknown particles or undiscovered symmetries might cancel out the vacuum's energy, like invisible cosmic accountants balancing the books. Others propose that gravity behaves differently at quantum scales, bending the rules in ways Einstein's equations can't predict. Then there's the radical idea that multiple universes exist, each with its own vacuum energy, and we just happen to live in the one where the numbers improbably align to allow galaxies and life to exist. What makes this paradox so maddening is that it strikes at the heart of physics' greatest ambition, unifying quantum mechanics and general relativity. The vacuum energy problem isn't some abstract curiosity, it's a roadblock preventing us from deciphering the universe's deepest secrets. If we can't explain why empty space isn't tearing itself apart, how can we trust our theories about black holes, the Big Bang, or the ultimate fate of reality? Yet hidden in this colossal mismatch might be a clue to something extraordinary. Just as the Michelson-Morley experiment's failure led to Einstein's relativity, the vacuum catastrophe could be pointing us toward a revolution even bigger than we've imagined. Perhaps spacetime isn't a static stage but something dynamic, its energy shifting like sand beneath our feet. Or maybe the vacuum's energy isn't missing at all, it's locked away in dimensions we can't perceive, like a shadow universe pressing against our own. The one thing we know for certain, the void isn't silent, it's screaming at us, begging us to listen. And until we decode its message, our picture of the cosmos will remain incomplete, a masterpiece with a gaping hole where the deepest truth should be. We walk through life convinced that space has three dimensions: length, width, and height, with time as a steady fourth. But what if the universe is secretly hiding more? String theory, one of the most ambitious frameworks in physics, suggests there could be up to 10 or 11 dimensions, all curled up so tightly that we'd never notice them in our day-to-day lives. This is the dimensional paradox, a cosmic sleight of hand that forces us to question whether reality is far roomier than our senses can grasp. Think of it like an ant crawling along a telephone wire. From a distance, the wire looks one-dimensional, just a single line stretching into the horizon. But if you zoom in close enough, you'd see the wire has thickness, a circular dimension wrapped around its length. The ant could theoretically move in that tiny, hidden direction. It just wouldn't get very far before looping back to where it started. Now imagine those extra dimensions aren't just around wires, but woven into every inch of space-time, coiled into shapes so minuscule they're a billion trillion times smaller than an atom. That's the mind-bending premise behind string theory's hidden dimensions. But why would the universe bother with extra dimensions if they're too small to matter? The answer might lie in the fundamental forces. Gravity, for instance, is perplexingly weak compared to other forces. A fridge magnet can defy the entire Earth's gravitational pull. Some theorists suggest gravity isn't feeble at all. It's just diluted, leaking into these extra dimensions like water seeping through cracks. Meanwhile, the other forces remain trapped in our familiar three-dimensional brain, a cosmic shelf where particles like electrons and photons are stuck. This could explain why gravity operates on such a different scale and why we've never detected these extra realms directly. Then there's the unsettling possibility that these dimensions aren't tiny at all, just invisible to us. Imagine living in a two-dimensional world like a character in a flipbook. You'd have no concept of up or down, only left, right, forward, and back. If a three-dimensional object passed through your plane, it would appear as a series of disconnected slices, first a circle, then a line, then nothing. Could our perception of three dimensions be just as limited? What if higher dimensional beings see us as flatlanders, oblivious to the full richness of reality? The paradox deepens when we consider how these dimensions might shape the universe. Some models suggest the Big Bang was less an explosion and more a higher dimensional collision, with our cosmos just one sheet in a vast cosmic stack. Others propose that black holes might be bridges to these extra dimensions, their singularities punching through space-time like needles poking holes in fabric. Even quantum entanglement, with its spooky long-distance connections, could make more sense if particles are actually close together in a hidden dimension, only seeming far apart in our three-dimensional view. What makes this paradox so tantalizing is that it's not just theoretical gymnastics. If extra dimensions exist, they could unlock answers to physics' biggest mysteries: dark energy, the hierarchy problem, even the nature of consciousness itself. The catch: we'd need energy levels far beyond our current technology to probe these scales. It's like trying to read the fine print on a billboard from a mile away. No matter how hard we squint, the details stay blurred. Yet the very idea reshapes how we see reality. We pride ourselves on exploring the vastness of space, but what if the real frontier isn't out there but coiled invisibly around us? The dimensional paradox doesn't just add directions to the universe, it suggests we've been navigating with a faulty map all along, oblivious to the folds and creases hidden in plain sight. And somewhere in those folds, the universe might be keeping its deepest secrets, waiting for us to think beyond the dimensions we think we know. Every time you take a breath, you're inhaling matter. Protons, neutrons, electrons, the building blocks that make up everything from your body to the stars. But there's a ghostly counterpart to these particles, a sort of cosmic evil twin called antimatter. For every electron, there's a positron with the same mass but opposite charge. For every proton, an antiproton. When matter and antimatter meet, they annihilate in a flash of pure energy, leaving nothing behind. And here's the puzzle. According to everything we know about the Big Bang, the universe should have created equal amounts of both. Yet when we look around, we see galaxies, planets, and coffee cups made of matter, with barely a whisper of antimatter to be found. This isn't just a minor accounting error. It's a glaring cosmic discrepancy that threatens to rewrite our understanding of existence itself. The numbers alone are staggering. In the first fractions of a second after the Big Bang, the universe was so hot and dense that energy constantly transformed into particle-antiparticle pairs. As things cooled, these pairs should have annihilated each other back into radiation, leaving behind a perfectly balanced void. But somehow, for every billion annihilations, a single matter particle survived. That razor-thin margin 1 in a billion is all that separates us from total nothingness. Had the scales tipped the other way, the cosmos would be an empty sea of light with no stars, no planets, no life. So why did matter get the upper hand? Physicists call this the Barrian asymmetry problem, and it's been haunting science for decades. One clue comes from Russian physicist Andrei Sakharov, who outlined 3 conditions needed for matter to dominate. First, there must be processes that treat matter and antimatter slightly differently, something called CP violation. Second, the universe had to be out of thermal equilibrium, allowing the asymmetry to freeze in place. Third, these processes had to occur before the universe cooled too much, locking in the imbalance. We've actually found evidence of CP violation in particle accelerators, but it's far too weak to explain the overwhelming dominance of matter we see today. That leaves us with 2 unsettling possibilities. Either there are exotic particles or forces we haven't discovered yet, ones that tip the scales dramatically in matter's favor, or our understanding of the early universe is fundamentally flawed. Some theories suggest antimatter might have been segregated into hidden regions of space, forming anti-galaxies beyond our observable horizon. Others propose that the mysterious neutrino, a nearly massless particle that barely interacts with matter, could hold the key. If neutrinos are their own antiparticles, a property called Majorana fermions, they might have triggered decays that flooded the young universe with extra matter. Then there's the wild card of dark matter. Could its gravitational influence have somehow skewed the balance? Or perhaps the answer lies in the moments before the Big Bang, in a multiverse where other universes ended up antimatter dominated by chance. The implications stretch beyond curiosity. If we ever harness significant amounts of antimatter, we'd unlock the most efficient energy source imaginable, with applications from medical imaging to interstellar travel. But more profoundly, solving this mystery might reveal whether our universe's matter dominance was inevitable or a freak statistical fluke. What makes this paradox so gripping isn't just the science, it's the existential weight. We're here because an unfathomably precise imbalance occurred when the universe was less than a second old. Had things been perfectly symmetrical, we wouldn't exist to ponder the question. That eerie fine-tuning forces us to confront whether our cosmos is the product of unseen laws or unimaginable luck. Every atom in your body is a survivor of that ancient annihilation, a remnant of a battle between matter and antimatter that shaped everything. The mystery isn't just about where the antimatter went, it's about why there's anything left at all. We experience time as an unstoppable river, flowing from past to future with absolute certainty. Yet if you zoom into the fundamental laws of physics, whether Newton's equations or quantum mechanics, they work just as well backward as forward. A movie of 2 colliding particles looks perfectly normal played in reverse, but a movie of a shattered cup reassembling itself jumps out as impossible. This is the time's arrow paradox, the baffling disconnect between the microscopic symmetry of time and the overwhelming one-directional flow we witness every day. The key to unraveling this mystery lies in entropy, the measure of disorder in a system. The second law of thermodynamics states that entropy always increases over time, creating an irreversible gradient from order to chaos. Scrambled eggs don't unscramble themselves, and perfume disperses through a room but never spontaneously gathers back into the bottle. Entropy gives time its arrow, its unmistakable forward thrust. But here's the cosmic rub. If entropy always increases, then the early universe must have been in a state of astonishingly low entropy, a condition so improbably ordered that it begs the question, why? Picture a deck of cards fresh from the factory, arranged by suit and number. Shuffle it once and it becomes slightly disordered. Shuffle it 1,000 times and any trace of the original sequence vanishes. Now imagine our universe as that deck. The Big Bang dealt us a miraculously ordered hand, all matter and energy packed into an ultra-dense, ultra-uniform state. Ever since, the cosmic shuffle has been increasing entropy, driving time's arrow forward. But who or what stacked the deck so perfectly in the first place? Some theorists suggest the answer lies beyond our universe. If we're part of a multiverse, our low entropy beginning might be a statistical fluke, a rare bubble where random fluctuations created the conditions for time to flow. Others propose that gravity, often overlooked in entropy discussions, played an unexpected role. In an expanding universe, gravitational clumping creates structure galaxies, stars, planets, a process that seems to create order but actually increases overall entropy by spreading energy more efficiently. It's like cleaning your room by shoving everything into drawers. The surface looks neat, but the system as a whole is more chaotic. Then there's the radical idea that the arrow of time isn't universal at all. What if the Big Bang wasn't a beginning but a midpoint, with time flowing in two directions from that singular low entropy moment? In this scenario, another universe might exist before our Big Bang, with its own arrow of time pointing the opposite way. To observers there, our future would be their past and vice versa, a mirror cosmos where causality runs in reverse. The paradox becomes even thornier when we consider quantum mechanics. At microscopic scales, particles don't seem to care about time's arrow. Quantum events are often reversible, with no inherent preference for past or future. Yet somehow, when trillions of these tiny reversible interactions pile up, they produce the irreversible flow we experience. It's as if time emerges from timelessness, like wetness emerging from individual water molecules that aren't wet themselves. What makes this more than just a physics puzzle is how it connects to human experience. Our memories, our sense of cause and effect, even our very consciousness are all bound to time's arrow. If entropy hadn't been so improbably low at the beginning, we wouldn't exist to wonder about it. This Goldilocks fine-tuning, not too ordered, not too chaotic, has led some to speculate about deeper principles at work. Could the universe's initial conditions have been somehow inevitable, or does their apparent perfection hint at something beyond our current understanding? Perhaps the most humbling realization is that time's arrow might be less a fundamental property of reality and more a side effect of our limited perspective. Like fish unaware of the water they swim in, we're embedded in a cosmic process that makes the past feel fixed and the future open. The universe doesn't need to remember the past, it is the past, with every moment stacked like layers in an ever-growing iceberg. As we probe deeper into black holes, quantum gravity, and the nature of space-time, we might discover that time as we know it is just one facet of a richer, stranger reality. The time's arrow paradox doesn't just ask why we remember yesterday but not tomorrow. It asks whether time itself is the universe's most profound illusion, a story we tell ourselves to make sense of the cosmic shuffle. And like any good mystery, the closer we look, the more questions we uncover. Imagine blowing up a balloon and watching it inflate faster and faster on its own, as if some invisible hand were pumping air into it against all logic. That's essentially what's happening to our universe. In the late 1990s, astronomers made a discovery so shocking it upended cosmology. The expansion of the cosmos isn't slowing down due to gravity, as everyone expected. It's accelerating. Something is actively stretching space-time apart, and we have no idea what. We call this phantom force dark energy, and it makes up a staggering 68% of the universe's total energy budget. Yet despite its dominance, it's utterly invisible, undetectable, and defies every intuition about how physics should work. The first clue came from distant supernova, exploding stars so bright they can be seen across billions of light years. By measuring their apparent brightness, scientists can calculate how much the universe has expanded since their light was emitted. But the data revealed something bizarre. These cosmic lighthouses were dimmer than they should be, meaning space had stretched more than predicted. It was as if the universe had stepped on the gas pedal halfway through its journey. The implications were staggering. Either Einstein's theory of gravity was wrong on cosmic scales, or there was an unknown energy permeating the vacuum of space, pushing galaxies apart. Here's where the paradox deepens. Normally, when you expand a volume, whether it's a balloon, a piston, or even the early universe, the energy density inside decreases. But dark energy doesn't play by those rules. As the universe grows, its density remains constant, like a magic gas that never thins out. This means the larger space gets, the more dark energy there is to drive expansion even faster, creating a runaway effect that could eventually tear apart galaxies, stars, and even atoms in a distant future cosmologists call the Big Rip. So what could dark energy actually be? The leading candidate is the cosmological constant, a term Einstein originally inserted into his equations to keep the universe static, and later called his greatest blunder. In this view, empty space itself possesses intrinsic energy, a sort of anti-gravity woven into the fabric of reality. Quantum physics actually predicts such vacuum energy, but there's a catch. The calculated value is a jaw-dropping 120 orders of magnitude too large. If dark energy were that strong, the universe would have ripped itself apart nanoseconds after the Big Bang. Alternative theories abound. Maybe dark energy isn't constant at all, but a dynamic field slowly evolving over time, dubbed quintessence after the ancient Greek term for the fifth element. Or perhaps our three-dimensional universe is a membrane floating in a higher dimensional space, with gravity leaking out and creating the illusion of repulsive energy. Some even speculate that dark energy is a shadow of another universe parallel to our own, its gravitational influence bleeding through unseen dimensions. The most unsettling possibility, dark energy might be a sign that our understanding of gravity is fundamentally flawed. Modified gravity theories like MUND tweak Einstein's equations to explain cosmic acceleration without invoking mysterious energy. But these struggle to explain all observations, leaving dark energy as the least worst explanation. What's clear is that this enigma isn't just a missing piece of the puzzle. It's a gaping hole where our theories break down entirely. As we peer deeper into the cosmos, dark energy remains the ultimate cosmic wildcard. Will it fade away, leaving the universe to expand gently forever? Or will it strengthen, dooming everything to a cold, lonely shredding? The answers, if they exist, lie in the darkness between galaxies, in the subtle warping of space-time itself. And until we crack this paradox, we're left staring into the void, wondering what invisible hand is writing the fate of the cosmos. From the quantum realm's spooky entanglement to the cosmic void's accelerating expansion, these paradoxes aren't just puzzles, they're flashing neon signs pointing to the boundaries of human understanding. Each one whispers the same humbling truth: the universe operates on a logic far wilder than our earth-bound instincts can grasp. Think about it: black holes that erase information yet defy quantum law, particles that change behavior when observed, dimensions curled into knots too small to see. These aren't flaws in reality, they're clues that we're missing something profound, like ants trying to comprehend the internet by studying a single fiber optic cable. What makes these enigmas so thrilling isn't just their strangeness, it's their refusal to surrender. For every paradox we've explored, there are a dozen competing theories, each more imaginative than the last. Maybe dark energy is the breath of a higher dimensional universe. Maybe entangled particles are tapping into hidden layers of space-time. Or perhaps, as the simulation hypothesis suggests, we're all just lines of code in an unfathomable cosmic program. The beauty lies in the not knowing, in the way these mysteries stretch our minds like space-time itself. And here's the kicker: every breakthrough only deepens the mystery. Solve the black hole information paradox, and you might unlock quantum gravity. Crack the antimatter imbalance, and you could rewrite the story of the Big Bang. These aren't academic curiosities, they're gateways to revolutions waiting to happen. The greatest discoveries often begin with a contradiction, a moment where the universe winks and says, "Your turn." So which paradox grips you? Is it the eerie dance of entangled particles defying light speed limits, the chilling silence of the Fermi Paradox, hinting we might be alone? Or the Boltzmann Brain scenario, turning your own consciousness into a cosmic roulette wheel? Drop your thoughts below. I'd love to hear which one keeps you up at night. And if your brain's buzzing with more questions, trust me, mine always is. Hit subscribe. We've barely scratched the surface of space's greatest mysteries, and the next episode might just bend your mind even further. After all, the universe doesn't hand out answers, it dares us to dig deeper, ready for the next clue.